additional assumption that the extension is always simple.
Oh, okay. So, yeah.
The differential type is smaller than the differential type of the target.
Right, right.
Of the sample.
So do you see how big the letters are? The rest.
Yeah, right big.
If you write that way.
Oh, you want me to write this?
This
large?
big.
Okay.
This big. And divide the board into two pieces.
Okay.
Yeah. I raised the board, but not too well. Should we begin?
Yes.
Okay.
Already.
I'll introduce you. I have to welcome you. Welcome, Andrey Minchenko from the Weizmann Institute, Israel. He's going to speak about central extensions of simple differential algebraic groups, or sort of.
Well, thank you very much, Phyllis, and organizers of the seminar for invitation. I'm very happy to speak again. So let's start. So this the topic is central extensions. Okay. I'll write bigger. Should I write bigger?
No, it's not. It's clear. Linear differential.
So I use abbreviation of LDAG for linear differential algebraic groups.
Yeah.
I'll define them briefly, but I would like to start with the motivating example. So this topic is a theoretical interest because, as experience shows, theoretical results on linear differential algebraic groups allows us to deduce several practical ones. For example, algorithm to find Galois group of differential equation. So this is one of theoretical results. Before I state it, I will need to go through some examples and definitions. So let me start with an example of motivating question. For example, yeah, so we can say let K be algebraic closed field. And look at FL2K. And we are interested in central extensions of this group. Central extension means that this is an epimorphism with a kernel being in the center of E. So this is central extension of SL2. Now, I'm not mentioning category in which we consider this holomorphism, but if the question is: are there non-trivial central extensions which are linear. This question is even interesting and wasn't. I mean, I didn't know the answer until recently, even for the category of abstract groups. So trivial central extension means that by trivial central extension, I will use this abbreviation. Domain E is isomorphic to SL2K times some A. Okay. And this map is just projection onto SL2K. There are non-trivial central extensions, but it is not known if they are linear. if it wasn't known if they are linear. My talk will be about what my talk will be about today is that I will classify such central extensions in the category of linear differential algebraic groups, and we will see that there are non-trivial central extensions. They are automatically linear because linear differential algebraic group. We will see that in the category, or better for the category of linear differential algebraic groups, which I'm about to define with corresponding to non-ordinary differential fields.
So you need
What do they correspond to?
at least one.
So they are over.
You
So
must have at least two. Derivation, is that right?
at least the derivation in our base field.
And what about for one? Doesn't work?
There are no
Then
all splitting.
Okay. Then also-
There are non-splitting or non-trivial extensions.
What does it mean? That for every
In fact, for every algebraic group, we will see that for every algebraic group, for every simple linear algebraic group, linear differential algebraic group, for every simple linear differential algebraic group over differential field with at least two derivations, we have a non-trivial central extension in this category. So E is also linear differential algebraic group.
and E is defined by equations with.
E is a linear differential algebraic group. I will remind you what I mean by this.
In Q, is E defined over Q?
Over K. So our ground field is K.
That's right.
Well, not this K. Maybe this is not very good. Let me write this as maybe L, because I will use K for ground field, and these are points. To speak about, so I started with the question regarding abstract groups, so I had to use points.
So bar is what? A differential quotient?
Algebraic
quotient.
Of course, we need to.
L is algebraic, but it has a set of derivation operators on it?
Yeah, if L is additionally differentially closed.
Well,
So-
we'll see probably precisely.
You will see when we
Yes,
do
I will
the
need to
definition.
define
Yeah, sure.
differential algebraic groups. So I recall that. So we have a ground field K differential field. Usually they ask it to be characteristic zero. And the classical definition is G is an algebraic. If it is given as a subgroup of some GLN, of U. So these are points, and U is a differential closed field containing K. Differential closed field. So this extension preserves the derivation.
And G is defined over K?
Yes, and G is defined by differential polynomial equations. the matrix coefficients over K. Oh, and so these are functions on
The polynomials of matrix coefficients?
Matrix entry schemas.
Oh,
oh, sorry, yeah, matrix entries.
okay.
So the polynomial equations with the coefficients in K
Went over.
with coefficients. This definition, although it is quite nice, maybe because it's very direct, but maybe there is a more convenient one, a more general one. So, particularly this definition depends on these two things. We have to choose. It's given. The embedding is given, so it's additional data, which we may not need actually. And the choice of this differential closure of differential closed field. In fact, we also don't want G to, in some cases, we don't want G to depend on this field. So we come up with this more general definition. Another definition. So I put this in quotes because it's not exactly this equivalent, but equivalence of categories estimates. So this is a it is an object or a dual. It is an object. The category dual to or opposite to the category of differential Hopf algebras with finely line generators. We can use finely generated, delta finely generated, Hopf algebras, differential Hopf algebras. Okay. So this definition may also works for arbitrary characteristic because we still have this object. So what's the relation between them? So we have functor of points. So proposition. Let us denote this category by small letter sub k of u. I didn't mention the morphisms, but in this case they should be given by differential polynomials in matrix coefficients. In this case, they're just homomorphism of Hopf algebras.
You can allow rational, differential rational.
No, you just allow one over determinant.
No, differential rational, yes.
It's differential polynomial
For groups, it's the same.
in Yij and 1 over det.
For varieties, it's not, unfortunately.
Yeah.
No. Yeah, right.
So, and this we denote just LDAG sub k. So this doesn't depend on the choice of you. And the relation is the following. We have the functor of points. So functor so what we do, how does it look like? So we take G and we assign it the points G of U. So here G is a Hopf algebra, and the points are the set of homomorphism, differential homomorphism into U. It can be given the structure of linear differential algebraic group in this sense, as an algebraic geometry. And we have this functor, and a good property is that this is the equivalence of categories. So here we use the theorem of field viscosity to show that. So in particular, we need to show that it is epimorphic on morphisms. If we have morphisms here, they are given so rational and differential. If there are groups, it's necessarily polynomial. So it gives us morphism of Hopf algebras. But if we, for example, want to, we have the same function from varieties. General varieties to the points. This functor would not be equivalence. Yes, like it is in algebraic geometry. So groups are very good in this sense. So we can generalize things. I mean, we don't have to depend on U now, nor the embedding. Just work with algebras. Now, once I define this functor, I maybe want to explain you the main construction example before my time's run out. So what we want, let me start with the representation of us. So for simplicity, we assume that G is equal. Oh, I forgot something. Remark. So there is a natural forgetful functor, the forgetful functor. From differential algebras to algebras. Has a right adjoint, has a left adjoint. So we can construct differential algebra starting from algebra. Just, for example, we want to know k of x over x squared minus 1. This is algebra, and we can produce a differential algebra. So the k is differential here. And then we just add so if you can suppose that delta is just one derivation, delta x, delta 2x, etc. And the mod out by the differential algebra generated by derivatives of this polynomial. This is a differential algebra. This is just exemplifies very roughly how this this left adjoint is can be described. And this gives us the embedding. This gives us this embedding. Embedding of the categories. Linear algebraic group over K into linear differential algebraic group. Okay. So we start with the Hopf algebra, finitely generated Hopf algebra, and we produce a differentially finitely generated Hopf algebra using this left adjoint. And in this sense, we can regard linear algebraic groups as a subcategory of differential algebraic groups. And from now on, I will speak about any algebraic groups as differential algebraic groups. It's just a special case. I recall you that this general definition works as well for arbitrary characteristic. We have this morphism for arbitrary characteristic. But I will later assume for safety that characteristic of k is 0, because I will use some results which require them. I mean, I'm trying to avoid this problem in the paper which I'm writing. This is one of the interesting cases, what happens in the case of positive characteristic. But today we will not consider this case. And now let me give you a hint how we construct central extensions. The main thought I want to get across today. So example. How to construct central extensions. So we start with SL2. So G is SL2. I can write this without any reference to the differential field U. Now, because I regard this as a linear algebraic group, and which is differential algebraic group, and consider the following representation. This representation was constructed in our paper with Alexey Ovchinnikov about representation of SL2. So I'll explain this on fingers without formalism. So what we have this block 1 by 1. We have this block 3 by 3. And we have 1 by 1. Let me denote this, say A of G. This is a usual three-dimensional adjoint representation of SL2. And here we have, I don't remember, we have some differential vector. So let me write this with, so we consider the case K is also differential field. So delta is just delta. So I just want to underline that this is a vector with which is actual differential polynomial, not just polynomial. Like this.
Let me look it up. Maybe it's easier for the audience to see the actual.
I'll give an example.
What does A of G mean?
Hmm?
A of G.
Whatever it is.
Oh, so, whatever it is.
No. So
it is what it is.
A refers to the three-dimensional representation of SL2. Algebraic.
Andrey, maybe.
I'll give an example of a coefficient, but I don't want to write that out all because it's too long.
It's fine.
So
why do you say that's G and what does 2 mean?
It's delta. It's partial.
Partial. Okay.
I just want to underline that this is actually differential vector. It contains of 3 entries, each of which is a actual differential polynomial, not just a polynomial. And here V.
So it's into a
and here
matrix over a polynomial.
And here, let me give you an example. So this is.
Oh yes.
So so if G is A, B, C, D, then partial A, partial D minus partial B, partial C. So this is what we have in the upper right corner. Thank you.
Oh, I see. So the original, oh, you have it there. G is A, B, C, D.
Yeah, so this is an example of such a coefficient. So they are about, they involve derivations. U and V are vectors involving derivations. And this is a reducible representation, it's in decomposable representation. And I will actually produce central extension starting from this representation. And then what we do? Yeah.
Andrey, just a second.
Okay.
Oh, yes.
Here we go. That's it.
Okay.
So this was for the case of one derivation. As I told before, there are no counterexamples in this case. So now assume we just want to change a little bit this representation. In the case when delta consists of at least two derivations. I'll suppose delta is at least two derivations, delta 1, delta 2, maybe more, but at least two.
Mm-hmm.
And let us write, I'll update on this picture, or maybe better to write again. Now consider this thing. Consider the same diagonal. Consider, so this vector is mu g delta 1, and this vector is bg delta 2. But
Does that look familiar, William?
we can't write anything here, anything special, because it would not produce a representation. But at least this representation on the first in this block and in this block.
That's clever.
And we put anything here, like C.
Yeah.
What do you mean we put?
This is a group. So
He's augmenting our
So-
Don't understand. Would you make a precise statement?
so this is a group.
What is a group?
Define this group.
It's
A
a
set
group.
of matrices whose entries look like this.
Yes.
It's a representation of.
Yes. So this block 4 by 4 is just
So it's 4 by 4.
parameterized by A, B, C, D.
So C is any entry.
Oh, C was from here. Okay, maybe I will put E. Okay.
So E is any entry from U.
E is any element, yes, from.
No restrictions on
Where's E?
U.
Okay, so here we regard as a set of points. Okay, U is differentially closed field, but then okay.
It's just one element.
That's the middle one.
Yeah.
Not the 3 by 3.
Okay,
That's right.
you can write this way
It's right there.
if it's better.
Is it the same as
So
this?
no change.
No change.
Which derivation do you use?
No, it's not the same element.
Yeah, it can't be the same, right?
4 by 4?
It is arbitrary element of the field.
Right.
Arbitrary.
No, I'm asking you the 3
What's
by 3.
3 by
3 by 3 is the same as before. Is this?
Using which?
Yes,
We're
yes.
using
This
which
matrix.
one
What
is
is
that?
matrix? Oh, the matrix has no derivation there, right? Okay.
Right.
Yeah, okay.
It's a three-dimensional representation.
So it's A squared, AB, B squared?
Yeah, okay.
Yes.
Now, what we have restriction.
So this is A and G in here.
So I see you're extending now.
Extend. This is not.
Extending the
This is not
matrix.
isomorphic to SL2 now.
Right, right.
Oh, sorry. It is actually isomorphic to PSL2, but it doesn't really matter because we consider three-dimensional representation.
Right.
We have -1 acting by 1,
Yeah.
but it doesn't really matter. So restriction of restriction to the to the span of first 4 basis vectors. It's clumsy, I know. For
Going down the column or across the row?
basis vectors. Gives us homomorphism. Denoted by, say, pi,
Oh, first one.
from E to PSL2. Right, because here we have just a group isomorphic to the image of SL2, which is PSL2. And what is the kernel of this? The kernel is just, you can check that this is just here 1, here 1, here 1, here 0, 0, and anything here. So pre-image of matrix 1 here. So we have 1 here, we have 1 here, which means exactly this type of matrices. And these matrices belong to the center of this group.
Which ones? The kernel.
Yeah, you can check that this commute with everything. With this, they belong to the center, which lies in the center. As for this, any questions?
So what does that matrix look like? It has a 0
This one.
all the way to start.
So this is just block 1 by 1
Oh,
with 1. This is 1. This is 1. This is identity matrix. This is vector 0. This is vector 0, and this is arbitrary element of the field.
Okay.
Could you explain this calculation?
Well, because what we do, we restrict the representation of this group E to the first 4 vectors, and we want to find the preimage of identity element under this homomorphism. So identity element means that here we have identity matrix.
Oh yeah, you'll get that.
Which automatically means you have identity matrix here, and here you can have anything.
Yeah, but
So,
it's not clear to people who don't see this actually this matrix.
No, doesn't help.
That's okay.
Oh,
The
because
audience who is watching, that is watching us, will have to believe you.
Well, because the AG has to have identity to identity, right?
yes,
Yes, but the rest, why the reason why he has zeros there comes from the actual from the actual
Yeah, that's right.
thing. That's okay. So they'll just believe you. And it's better if you write all the entries.
most likely there is a better explanation, but
It's okay.
I couldn't find it right now. So we have a central extension, correct?
Mm-hmm.
Why is it not trivial? We have a central extension. This group is a linear differential algebraic group because you can see it's given by differential polynomial equations. Actually, the equations are between this element and this element.
Why it's not trivial isn't clear.
Well, because
Why doesn't it split?
Hmm?
Doesn't split.
why doesn't it split?
Yeah.
I'll explain. This is not, maybe this is not so easy to see, but we just need to notice one property of splitting extensions.
Okay. This is not split.
So notice that, so the fact is that this pi is not splitting. Is not splitting. Why? Because know that if E is isomorphic to ESL2 times GA. Well, the kernel is isomorphic to GA. O means from there.
They're doing dancing up there or something. The ballet class, member of graduate division.
So it splits, then E is necessarily isomorphic to this product. And then we notice that
The kernel is GA.
well, that if E is isomorphic to this product, then E inverse of maximal torus is commutative. So this is maximal torus. So diagonal. Actually, not diagonal, the image of diagonal. Okay, the preimage of maximal torus. So we have when A. So when B and C are zeros, is commutative. Must be commutative. The elements side of diagonal B and C.
U and B.
Cross diagonal, whatever you call it.
Yeah.
It means you. Would you write it down instead of saying it?
So we can parameterize all elements here by say M, A, B, C, D, E, right?
Yeah.
Yeah.
So the preimage of so maximal torus.
So what is A, B, C, and D? These are the matrix extensions of a cell.
Yes. I already read this before. A, B, C, and D.
So pi is it's rational, it's not just differential rational. It doesn't involve any derivatives, in other words.
No, it doesn't.
It doesn't.
How do you know?
A, B,
Oh,
C.
E is arbitrary.
I'm wondering what you're going to do about pi inverse of t if you don't know it's a mapping of algebraic groups.
E itself is not algebraic. So the preimage is not algebraic.
So when you go ahead and say what you're going to say about the pi inverse of a maximal torus.
Must be commutative, which is not. But it's not commutative. Right? Maximal torus is commutative, and if E is isomorphic to this guy, then the preimage of maximal torus is just torus times
Yeah. Why does it?
But it's not commutative. You can just
Why would pi inverse of t split into a direct product? Pi inverse of the whole thing.
Well, in this case,
T is in PSL2.
pi is just
T is
the projection on
T is in it's
T
pi in.
is PSL2.
Why?
Because the map pi goes into PSL2.
Oh, pi goes into PSL2.
Yes.
That's right. That's right.
But one can see
Yeah, then that would be true.
that
But why would pi inverse be commutative also? Because it's a direct.
yeah. So T is itself commutative, and its preimage is just GA times T.
Why is its preimage? That's
Because,
what I'm asking. Why does
because,
that a direct product?
because if pi is splitting, then E is isomorphic to this,
That I know.
and pi can represent as projection on the first factor.
Yeah.
And in this case, the
Why
preimage
can't it
of
lie
anything,
across the direct product?
in this case, the preimage of anything is just this factor times this times the set we took here.
Well, okay.
And so if you start with something commutative, the preimage will be still
Even
commutative.
the preimage is just a torus times GA.
Yes,
That's the
yes,
preimage.
yes.
No, but well, I was
So-
just not absolutely clear on why the preimage should be a direct product. Just because the ambient group is a direct product.
Because over each fiber, you get all of GA, right? So over each point of fiber is all of GA.
No, that's true. It's the inverse image. Okay. Okay, yeah,
I
thanks.
think it's because of
Yeah, it's fine, yeah.
That pi inverse of t
Yeah.
is not equal. Actually, computation shows that if you commute m a0, a inverse 0, 0 with m b 0, b inverse 0, 0. So these are elements of in pre-image. Then you'll get delta 1a. Maybe I should write it in different place. Then you'll get partial 1a, partial
You're
2b.
moving to that counterexample. Pardon me. You've got the
Minus
constants of one of the derivations and those constants of another. I guess. Maybe not. No, it's delta 1. I can't see really.
A, B. So these elements are definitely in pre-image, and we see that their commutator is not 0 in general. Because this difference is not 0 in general, if A and B are different. So you see that if delta 1 were delta 2, then it would be 0. Like if there was just one derivation. This agrees with the fact that I told before, that everything splits. I mean, central extensions split over SL2 if we have just one derivation. Actually, what I did, I produced some non-splitting central extension of PSL2, not SL2. But it's easy to get a pullback and produce a non-splitting central extension of SL2. Okay, we have this SL2 covering. We get pullback and it will be central extension of SL2. It doesn't matter.
I think you said it before, but when you say extension of PSL2, you always say extension of PSL2 by GA. Is that always what you're thinking about?
No.
Here PSL2 by GA.
But it doesn't have.
It's almost have to. Because you see, if you have more than two derivations, you can get other pairs like delta 1, delta 3, which gives you extension by GA squared.
Oh.
And so the extension, there is, so the theorem, which will be, there is a universal central extension,
Okay.
GA times the number of pairs of m derivatives. That is, in the power of m times m minus 1 by half.
Oh.
Okay. So now let me.
Do you have anything written up on this, or
Pardon?
anything we can see in print?
Not yet, unfortunately.
Not yet.
I have some questions which I'm thinking on. I will mention them.
Okay.
Doesn't this sound bothering you?
Does it bother you?
A little bit. Because I'm closer. So let me give a couple of definitions when I say the theorem. So let me start with the functor of constants. Say L constants.
What is the symbol before constants?
It's L. So
L.
let L be a subset. Let L be a subset in K delta. The vector space over K base field with basis of delta. It doesn't hurt if you assume that this is a Lie subspace, but it can be any.
Any subset.
Any subset, yeah. And we can consider, so A is a, so G, so A is a differential soft algebra. And we can consider this quotient. So we can consider the quotient by the differential yield generated by these elements. So what means that we just apply every element of L to elements of A, generate the differential ideal, and motion by this ideal. So we have this natural homomorphism, and it corresponds to taking constants on the group level of points. So it corresponds to the function of taking L constants. So F G. If you take so U points, it will be just G U L. Right? So the homomorphism. So this map of algebras. If you consider the map of spectrums, you will get the map of inclusion of constants, the points which are constant with respect to derivations with respect to operators from L. So this embedding into G of U.
So you're using the equivalence between LG, AG with the U points.
Yes, actually.
That could contain one. But that's all right, I guess.
I don't need the equivalence. It just if we have a map of algebras, hence we have an opposite map of points. So this is opposite map of points.
You really mean apply L to all the elements of A and you set them equal to 0 in the image?
Yes.
You don't care if it contains one? The differential ideal?
No, it doesn't contain one because we take it in.
What if it's delta and something and one is the derivative of something? I don't understand the symbolism.
Yes.
So G here.
What do you mean?
Andrey, G here is the differential rate group corresponding to A, right?
Yes, G corresponds to A.
I'd just like to know what that differential ideal is.
G
What are the
is the differential
generators?
half algebra,
Yeah.
right? So G is by definition in the dual category, right?
Yeah,
So that A is the coordinate ring of G.
So he meant something else.
Yeah.
I thought it was.
Andrey, could you write down the definition of
Once you have a
We don't understand the differential
We
ideal.
don't understand the
What
goal.
do you have what?
We don't understand
A
the
Hopf
whole
algebra.
thing.
Half algebra.
Yes,
Would you please
then the
rewrite in
linear
different terms?
differential algebraic subgroups are objects in
What-
the category of
Forget about the
the dual
category.
of the dual
Just write down
of
the
the
formula.
value,
What's
right?
the-
So what I'm saying is that
all algebra.
Oh.
So the half algebra is the coordinate of G.
Ah.
So
for
that's the
for
correspondence.
every A there is one G.
Yeah.
So for example, you have all the G.
You have
No, no,
Well, I'm
for
not sure what
example,
it's
define the
unique to. Maybe-
symbolism,
Oh,
differential
yeah,
ideal
There
generated
is
by
one-
LA.
Oh, okay.
Just a
What's
symbol.
that?
So-
What is it?
so L is
L is a lead
so
vector
LA
space.
is what is set consisting of
Not necessarily. It could be delta.
Okay, fine, sure.
Could be.
partial
I just want to know the definition.
partial tilde x,
Yeah.
where
X is an A.
partial tilde is in L
L.
and x is in the A.
What is delta x?
Suppose delta X is 1.
No, what is the meaning of delta x?
Yeah.
A is a differential half algebra.
Is delta applied to x or what is it?
What is it?
Yes, it's
It's applied.
because
It's applied.
we have an action of
Yes,
Don't
but
explain why. Could you explain what it means? It's
Yeah.
applied or not?
yes applied.
Okay, that's
what if delta X is 1? You don't care.
It with the whole thing.
it's wrong. It's a wrong definition.
It's really,
It's supposed to mean something else.
yeah, I think so. I mean, if it corresponds to that, it's got to mean something else.
Wait,
I don't understand.
I don't see what the quotient there has anything to do with the functor.
Well, that's a good point too.
What was that?
Could you explain what you want to achieve?
What do you want?
Yeah, I
To,
mean,
what do you want it to be?
We'll
There's no need-
modify the definition
There's
together.
no need to
Sure.
write A mod, the bracket of L.
What do you want? Andre?
so
Right, when you're given A, you're given L, so therefore you're given a G, therefore you have this map.
Yeah, the bottom
so
line is not-
these are L constants. So
yeah.
What?
Yeah.
Yeah, but is that what you want?
I mean, if you have if we have this embedding delta, say L is just one, consists of one element. Right? We have the embedding of points.
Right.
What the corresponding map of Hopf algebras?
All that I think I'm with. I'm just not
Yes,
with
so
that
you
symbolism.
need to add extra relations where you take the
Oh,
No.
the generator, yes, generators
Yes.
of the Hopf algebra,
right.
and add the relation that the derivatives are equal to
Yes.
0.
Exactly.
No, what is G? Would you explain what G is?
Absolutely what he wants.
G,
Never mind
G,
what
G
G
is
is.
a linear differential equation.
Yes. And what is its coordinate ring?
A.
Differential coordinate is A.
A.
Right. Okay. So what is this A mod bracket LA doing here in the
Forget
function?
about it, it's already we passed through it. It's
Oh, you
incorrect.
passed through. I thought that was a
It's
problem.
incorrect. It's
It's
incorrect.
incorrect.
We just erase it.
Wait, I don't understand.
He is not accepting your.
Andrey,
That's true,
because the simplest counterexample, take A to contain an element whose derivative is equal to 1.
Yeah.
Then immediately you'll have 0 in the
Yeah.
right hand side.
Do you
Yeah,
care?
but
That's it. So you map A to 0. Just even if you have a few, if
It's
you
going
have
to almost always be 0 if
yeah,
A is
because you
rich
have an
enough.
element in L
Yeah.
or
that element will be a constant function.
doesn't matter, but you move out and you get 0.
No, you get the whole ring if 1 is in the
Andrey,
differential
but
idea.
do you really need to have a coordinate-free
So you get
definition?
0.
Do you want a coordinate-free definition, or are you okay with coordinate definition?
I want to get a free definition.
Coordinate-free definition.
But I really.
I think it works.
No, he doesn't want that.
I think in this setting it works, right? In this setting.
This is incorrect.
Incorrect.
Yeah, no, I think in general it's incorrect, but if you're working with a group, I think it works, right?
No, I'm
Take a
not.
few here who
Definitely your function is
Right.
not responsible.
No,
Yeah, but in
okay.
that case, A would be the coordinate, the differential coordinate ring of
K to be C
We know
of
what
x.
that is.
Okay? In that case, x derivative of x is equal to 1.
One.
So,
Sure.
okay? Then
But
A
then-
contains 1. So
I don't
immediately
care. That has nothing to do with the functor FL.
he moves out by the ideal.
No, that's not how he constructs a functor. Functor is given by that.
That's okay. He wanted to give an algebraic description.
The functor is fine, but that is wrong. A into A mod LA.
Yeah, but
What is wrong? I mean, okay, if it is equal to 1, it equals 1.
If that equals
equals
that,
0, equals
because
0.
that first
It doesn't
description
correspond
doesn't
to-
match what
There's no correspondence he mentioned here. He never mentioned
He did
anything about
mention.
that
He
thing.
did.
it
and the
corresponds to
functor.
the functor, you see?
Yeah, and it doesn't.
But what it says A. and M.
Let's stop the formalism
Right.
of reading.
Yeah, it's wrong.
So for example, what if you take A to be just the differential polynomials, right? A is to be, so all alpha in space, all alpha.
Yeah, but I take K to be equal to be C of X.
You know what? Actually,
C
Of X, so that derivative of X is equal to 1.
Yeah.
So you mod out by an ideal that contains
but
1.
then you have to take like the free object. You have to take like the polynomial.
That's what I'm saying. But that will choose a generator, so he doesn't want to choose
no,
generator.
I don't understand. For
He
example,
doesn't want to take
for example, okay,
He wants coordinate
let's start with this group. 1, x, 0, where x prime is 1.
Yeah.
So when you take constants of the group, what do you get?
Oh, wait a minute. That's not a group.
You get just 1.
That's not a group.
That's not a group.
That's not a differential algebraic group.
Okay, sorry.
X second is 0.
Yes, that's okay. That's linear operator. Yes. Homogeneous operator. Andrey, why don't you want coordinates?
Yeah, coordinates are lovely.
Yes.
Because they depend on the bearing.
So
Well,
No, no,
then
no.
you ask yourself what does and
No,
what
no, it
doesn't.
should be,
depend on the
it should be some
event.
way. I think I don't. I still don't understand the problem. Maybe I'm the rest of jet lag is. I
That could be. Yeah, yeah.
Of course, there's
That's a long trip.
Okay.
Andrey, what is
What do you want
what
to
is
do?
square brackets?
Differential ideal generated by this.
Okay, don't forget about just erase it.
Andre, why not stick with the bottom line?
Yes.
Let F
That
sub
would
L of
depend on
G
you.
of U
See, the thing is
equals
that,
G.
that still have U in it. He doesn't want U.
Oh, you don't want U. But as Omar showed us, there's a lot that depends on you. Choice of you.
Okay. Let's for a moment forget about this.
But your differential algebra isn't differential.
Well, let's just choose generators. And we'll see how we can get rid of them later.
That's all. Let's just move on.
Move on to what you want to construct, and you can fill it in later.
Central extensions.
But Andrey, by the way, so I have a concern. Doesn't taking taking constant depend on generators actually? It does depend on generators because you can, if you take a conjugation, you have different generators. You're no longer
Yes.
constant.
It's not independent of the choice.
So that actually that thing is has to depend on generators naturally.
By generators? What do you mean by generators?
Of Hopf algebra.
Algebraic.
So how can you induce? How can you require constants? Choose generators. So
That's true. You have birational
and the derivative
equations.
is equal to 0 for each
Delta
coordinate.
birational functions are not going to be independent of the choice.
But if you choose a different set of generators,
Then you will have a different.
you lose.
A lot.
If you do it over a field K that is not constant,
Right.
you might end up with a non-constant group.
Right,
So
right.
it's not this is not a coordinate-free notion.
But
To
maybe
start
he
with.
doesn't mind. He'd call that descends to constants or something. Maybe he doesn't care if you change the generators the way.
Don't worry, let's just choose generators and forget about it.
Okay.
Let's do concrete terms without any abstract nonsense.
Okay. I'll make this up later, but it doesn't hurt if we. Anyway, I wanted to talk about extensions of algebraic groups where we don't have any constants.
That's okay.
Central extensions. I recall that we have, this is a short exact sequence.
And that actually is not a functor. That thing is not a functor.
That thing?
No, below. Taking constant points is not a functor.
No.
Because you take a morphism, you get a conjugation.
Right. Oh, lovely, yeah, right.
But doesn't matter. Maybe you don't need that fancy language. Maybe you can cook up something
You
with
be
coordinates.
careful in differential algebraic geometry.
No, I can't. I don't. Anyway, I didn't want to talk about extensions of constants. I wanted to talk about extensions of algebraic groups.
Yeah.
And this definition